Welcome. In modern artificial intelligence, the concept of an agent is fundamental. It provides a powerful abstraction for designing and analyzing autonomous systems. An agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. Let's break this down. Formally, an agent's behavior is described by the agent function, which maps any given percept sequence to an action. The agent program is the concrete implementation of this function. Our goal is to design a rational agentone that, for each possible percept sequence, selects an action expected to maximize its performance measure. To design a rational agent, we must specify the task environment. A common framework for this is PEAS: performance measure, environment, actuators, and sensors. This framework forces us to define the problem precisely, clarifying what the agent needs to achieve and what tools it has at its disposal. Let's apply PEAS to a self-driving car. The performance measure includes safety, speed, and legality. The environment is the road with other traffic, pedestrians, and signals. Actuators are the steering, accelerator, and brakes. Sensors include cameras, LiDAR, GPS, and accelerometers. This defines the operational context completely. Environments have several key properties that determine the required agent design. Is it fully or partially observable? Is it deterministic or stochastic? Episodic or sequential? Static or dynamic? The answers to these questions dictate the complexity of the agent program needed to succeed. For example, a sequential, partially observable environment requires the agent to maintain an internal state. Let's look closer at the components. Sensors are the agent's input channels. For a software agent, this might be API calls or reading files. For a robot, it's physical hardware like cameras or microphones. The sensor model defines how the agent receives information, including potential noise and uncertainty, which is a critical factor in partially observable environments. Actuators are the agent's tools for affecting the environment. A robotic arm has motors, a trading agent executes buy or sell orders, and a web crawler makes HTTP requests. The actuator model describes the effect of an action. An action might not always succeed as intended, a concept known as stochastic effects, which the agent's logic must account for. The heart of an agent is its architecture and the program that runs on it. The architecture is the computational device with physical sensors and actuators. The agent program is the function that implements the mapping from percepts to actions. We will now explore a few fundamental types of agent programs. The simplest agent is the simple reflex agent. It selects actions based only on the current percept, ignoring the rest of the percept history. This is implemented with condition action rules. For example, if the car ahead is braking, then initiate braking. These agents are extremely fast but have limited applicability, as they cannot handle partially observable environments. To handle partial observability, an agent needs to maintain an internal state to track the parts of the world it can't see. This is a model-based reflex agent. It uses a model of the world to understand how the environment evolves and how its own actions affect the world. This internal state is updated over time using percepts and knowledge of action outcomes. Knowing the current state isn't always enough. Goal-based agents use goal information combined with their world model to choose actions that will achieve those goals, often involving search and planning. Utility-based agents are a refinement. They use a utility function to quantify a preference among different world states, allowing for rational decisions when goals conflict or have uncertainty. In summary, the agent abstraction provides a structured way to think about autonomous systems. By defining the environment with PEAS and choosing an appropriate agent, architecture from simple reflex to utility-based IDWI can engineer rational solutions to complex problems. The next step is to incorporate learning, allowing agents to adapt and improve their performance over time. Thank you.